Last week we ended up talking about some really basic data structures that are available in most programs, most C programs. The reason for that is there's a number of instruction primitives that exist for operating on a lot of the stuff that we worked with last class. This class will dive into more complex data structures, and I'm going to walk through some of the examples that I built using GDB again. So we'll get to see the combination of how the structures are kind of assembled at the data level. Some of you might be familiar with it. Some of you might just be more familiar with the application programming interface to those things, but not necessarily familiar with how C and assembly and stuff like that organize those things in a memory. So trying to provide you that information is going to be the point of this lecture. And the other key thing is that we'll be dealing with a lot of the dynamically allocated structures. So end of last class, we covered, we looked into a data structure, one very simple data structure that had a handful of elements. I'll reuse that same one as the basis for the structures we're putting together today. But also, we did go and look into a little bit of dynamic allocation as well. We just touched on it briefly using a two-dimensional array where the first dimension was an array, but then the second dimension was actually defined by a pointer to another array. And you ended up having 3 disjoint arrays of 12 elements each that weren't organized immediately one right after the other in memory, like allocating a consolidated array was. So in this case, a lot of the higher level languages you will run into, and especially languages that very quick backdoors are written in, the frameworks that are used. So really common approach to doing networking for malware is not necessarily to write all the really low-level networking primitives that you can get out of like the WinSock library or something like that, but actually use higher-level frameworks and higher-level libraries to wrap a lot of network and network management concepts. And those things typically rely upon various linked lists and trees and other data structures like that. So we'll start with linked lists. This is back to data structures for many of you. So I won't go into the whole data structures explanation of it, but one of the, it is one of the core data structures, and we'll say that. So you run into this one a lot. Many of you who deal with like kernel programming and stuff like that have probably seen this a whole lot, or I should say I've seen them used all over the place. Just like in the lecture from earlier this week, we end up using the common runtime allocation calls. The data organization doesn't actually reflect the organization that the programmer uses in order to access these elements. So while the program is going to treat them as it's going to treat it like an array for the most part. That's the outer level of the program is going to treat this as a sequence of elements, basically, or a sequence of data. Under the hood, where these things get organized in memory could be all over the place. One could be, like number 3, could be located in a memory address that's actually lower or earlier than element 1 and stuff like that. So they could be all over the place. And it doesn't necessarily suffice to just dump the data section of memory and then try and look for a contiguous block that has everything I'm looking for. Ends up being our job as reverse engineers and malware analysts to try and rebuild what the author's data structure was by looking at the code and doing the static analysis on the code like we were doing with the disassembly, or even doing runtime analysis and stepping through the program and watching what it does. And so I'm going to jump over here, and I'm going to show. So I put together 3 examples of more complex data structures that are all built off of this same thing. So this is that small data structure I demonstrated on Tuesday, what I've pretty much defined for this one is this is an address like 32 bits. This is a character, and we'll pretend just so that we can assign like a role or a purpose to all these things, so it kind of makes a little bit more sense. We'll say that like B means block and A means accept. And so maybe this ends up being a data structure that's managing a set of like tunneling rules or something like that. It's a really common approach that attackers will use in trying to get access to your network. Is they would like as much access to all the computers on your network as possible. Many of you are familiar with the concept of firewalls. And if I have a firewall between my internal network and the internet, then a lot of times the network traffic coming from the internet and entering my network is limited, so that the only things that are allowed to be talked directly to are a web server or a mail server or something like that. But if I have 20 employees and they all come in every day and they plug their laptops into the internal network, I don't want somebody to be able to scan my network connection and find out that like there's all these Windows machines that are plugged into my network that they can directly access from the internet, right? However, most attackers would really like that to be the case. Most attackers would like to be able to directly access whatever the end user Windows machines are on a network. So a common approach that they may do is if they do find a vulnerable machine that they're able to get a backdoor on, a really common approach is to install some sort of tunneling tool. And that's basically a tool that'll maintain a table of other machines that they can access on the immediate network from that machine. And so one approach that you might run into is a tool like that being used in managing its data set in one of many different data structures. Trying to figure out what is going on involves analyzing the data as well as the code. And then this allows us, for instance, network TCP port, right? So this allows us, for instance, to simulate or mimic a backdoor or a tunneling tool that has this type of functionality. And then it also associates with each one of those a network port to go and connect to. And so they might, for whatever reason, have some sort of like permissions set up so that they decide that they won't forward some package through this tunnel to a certain IP address, and other times they will. And there might be various OPSEC reasons for that. So the one we'll start with is this one right here, which is the linked list structure. And as you can see, it's really just two sub-elements. One of the key ingredients here, though, is that I'm taking the structure I built last Tuesday, and then I'm adding one more layer underneath it, or one more layer on top of it. And the layer is basically to encapsulate that data structure, and then afterward add a pointer to the next item in the list. So basically, this right here ends up being that data structure that's holding my IP address, port, and modifier, and then this ends up being that next pointer. And all it is it points to another item. Typically, the most common approach to this, and we'll analyze. We'll analyze this code right here. The most common approach to implementing a linked list is that when nothing is in the linked list, when it's empty, to populate the pointer with null. So basically have the pointer be null, or have it point to something that ends up being like an empty pointer or something like that. Many of you probably learned that from data structures. So that when I start my program, before I've added anything to it, this pointer ends up being null. And then what I do is I run this function which takes as input that pointer, and then also whatever data I would like to add next to it, and then it returns a pointer. So what I ended up doing here was I wrapped the data allocation or the memory allocation call as well as the insertion operation into one function. And so from the author perspective, from the author's perspective, most tools, you'll end up seeing this type of information hiding behind the scenes. They don't want the person who's, or I should say they don't want the code that's making the function call to add, say, new data to a list to also have to pre-allocate space for that data ahead of time and then pass that information in. They want to do all that functionality behind the scenes. That's a really common design pattern. And so that's what we end up doing here, is we end up allocating new space here. I use the new operation, but also the malloc is fine. Then I populate it with the 3 arguments that were passed to me right here. So, and then if the thing given to me, if the list head given to me is actually a null pointer, then what I end up doing is I just return my new object as as the resulting pointer. Otherwise, if there were other elements already in the list, then what I do is I go to the end of the list, and there's many different ways to do this. Just adding stuff to the end of the list. Sometimes people may actually have an insertion where they're trying to keep ordering of the list, which would make this logic here a little bit more complicated, but not that much more complicated. And then after I've added my element, so after I've fixed up the list so that it has my element, then what I end up doing, which is what's going on right here, is I find where it belongs, and then I put it where it belongs. Then I just return the head. And so this ends up giving me the property of being able to turn this call into something that, from an author's standpoint or from a user's standpoint, ends up being the same line of code, whether or not I'm dealing with the first element or the last element. So, and really that's kind of the goal here, and that's why that stuff gets hid behind the scenes. What I can do is I can run this program. So and we'll turn on the debugging stuff so that I can look at the source code, and it'll actually do a bit of analysis for me of the data structures as well. So again, I can list main, so I can show the source code that's associated with the main function. You can see all that stuff there. Basically what I'm just trying to look for is I want to set a breakpoint in the code so that the data is loaded in memory and then I can analyze it. So I'm going to set a breakpoint like right here, I guess. So break 117, and then I'm going to run it. So now it's waiting to run this code. So whenever you're using a debugger like this, what it ends up showing is the line that comes after the line that you are actually breaking on. So the last thing it ran was this. The next thing it wants to run is this, and I'm actually at a cursor right between the two. So you, generally speaking, can't interrupt an instruction mid-instruction. And then when you're doing it this way, they even go so far as to force you to only do it on a line-by-line basis. However, if I was doing disassembly mode, which you can also view, then I would be able to break on individual lines of disassembly, or I should say individual instructions as well, but no smaller than individual instructions. So what this ends up having is this here, L, actually it might, let me see if I can do a reset here. No, I can't remember if I can reset in this or not. I should have probably done this though. So what we'll do is we'll break all the way up here at like 108 or something first. So we'll break there, and what I'll do is I'll print L, and L is the null pointer. So then what I can do is I can do next, and then I can print L, and it's still like that because again this has not run yet. But then if I do next again, then it drops down to the next line, right? And so then I can print L, and now L actually has a pointer stored in it. One of the nice things about GDB is that if I'm using a data structure in GDB, or I should say if I have the source code to the program that I'm analyzing in GDB, then I can actually I can inspect the data in the data structure using the names of the different sub-elements of the data structure. So for instance, you can see this thing right here, and then you can see that the next item is actually the null pointer, so it's a single element list, right? And so then I can just do next. And so then I jumped again, so you can see this line got executed, this one, and this one corresponding to these three right here. And then we print it, and so this right here stays the same, but then this over here ends up getting populated with the next pointer, right? So what I'm going to do now is I'm going to do, if you remember, we looked at this and it was 8 bytes long was the size of the data structure. So it's 8 bytes for the data structure, and then this is another 1, 2, 3, 4, 6. So this is 6, 7, 8, I think. So it's, we'll say 16. So we'll examine the stuff that's at L, right? Or actually at star L. Yeah. Trying to remember now. Sorry. I'll just print L really quick just to see. Yeah. So L is pointing to this. So this is doing the dereference for me. So what you're seeing here is I put in this 172.20.22.1. And what it ended up doing was I put it right here in this field, right? And then it's got the 61, which is A. And then it's got that padding that we saw before. And then following that, it's got the port that I put in there, which is 3333. And then following that, we've got the 8 bytes that represent the address of the next item to go to. So how I would look into this actually is I could look at it this way, I think, or no. It is word giant. So G, and this ends up giving me, I'll actually just drop it down to 2. So I just multiplied the size that I'm going to look at by 8, which means I have to divide the number, the count, by 8 in order to get the same data. So this right here ends up being the data that is representing that next item. So the next item in my list is there. And so I would be able to use that to go and manually walk through my linked list in memory. And these are the types of things that you'll want to look for is a constant attempt to say, or I should say a thing that looks like it's a pointer to program memory or local memory. So in this case, one of the indications that I have while this is running, that this is a pointer to local memory, and this isn't, and these aren't, right? And this isn't, and that's not, and that's not, and that's not. So these, like, the top half here, only one of these is likely to be a pointer to my local data memory. And the reason I know that it is because this one right here at the top right there ends up being more or less within the same numerical space, so very close in numerical proximity to the other data I'm analyzing. So I got some data from my program, say maybe from looking at an instruction that was running and trying to do something to data. And then I looked in memory to see what it was working on. And I managed to find out that what it's working on is a block of data that looks like this. And I can't really make heads or tails of what this is on the left-hand side if I'm looking at it in this manner. But on the right-hand side, if I formatted it in the manner that's identical to my system addresses, then I can see very clearly that that looks like it very well might be an address. So I don't know for sure from this. I don't know for sure until I start messing with it. So then, what I might end up doing is I might end up doing this. And then this shows another one, right? So another blob of data that I can't figure out what it is.
It's already recorded.
Yeah, it shows up here, mainly because when I ran the new a bunch of times, so I ran the new in sequence, what it does is it tries to allocate memory that's close, So this is all going to be located in the large range of memory, and that's a really good observation. He was pointing out that this line that I just showed right here is actually this line that was right here when I dumped out a larger section of memory. And in a lot of cases, you're going to end up analyzing data structures that are allocated from the same malloc heap or the same pile of free memory, basically. And that pile of free memory does have a finite window where it lives, or I should say where variables live within it. And that's why you can make some of these conclusions just by looking at the data structures. Like, for instance, this one it's not going to be allocated in an address where this stuff is all set to like all sixes or something. It's going to be allocated in an address that's very close to where this one was allocated, or very close to where this one's allocated. And so then the next one, so if I walk through this sequence again, because also the other thing that I've learned here is that this right here is all zeros, indicating a null element, right? So what I might do is I might run next again, or might step through it. So step through the sequence of assembler steps. This is really going to look like a loop in many cases, or at least a sequence of repeated calls when I'm looking at this in a disassembler or in a decompiler. So then, I can go back here and look at this, and then I can see that after I ran that, it changed memory again. And it changed memory by putting an address here. And so then if I go there, then that thing now shows up with some sort of random non-discernible data here that doesn't really have any huge correlation to here or here. So those don't seem to be offset records or anything. But now this new one has this null pointer set to it. So I'm walking, I would be walking through a sequence of calls that I think, can I do this? I'll have to remember how to is show. There we go. Okay, I'll deal with that later. But anyway, I'll just go back up to this. So what I ended up showing, so this is the third one now. And if I was to go back to here and dump out the 16 here, right? So now you can see there's like another line that's been added here, right? And then it also has like this random stuff. So, but yeah, so that's kind of what you're looking at. The other thing I will say that's interesting about this is that you do see these things. So these numbers right here, and if I'm not mistaken, yeah, that's the yeah, this right here is actually the what would it be called? You'll see this implemented differently in different systems. This is also another good indicator to point out, is that I'm running new in order to get memory out of some sort of pool of what's defined as free space for me, right? Free memory. Every time it's doing that, it's taking a little bit of memory, and then it's giving it to my program. But it needs to keep track of what it's given to my program, because I know that in the future, I want to run a delete operation in order to free up that memory. So what's going on here is it allocates the pointer right here. And then in the space immediately before the pointer, it actually allocates another byte. So instead of allocating 32 bytes, or whatever it is, yeah, instead of allocating, yeah, it's like, it's not another byte, it's another like 16 byte blob. I can't remember what it's called. So instead of allocating this like this single 16 byte thing here, which this is 8 on the left and this is 8 on the right, it actually allocates a slightly bigger chunk and puts this little like information header in front of it. And part of that thing tells how big this whole chunk's going to be. And I forget what the number on the end there indicates. But the idea here is that it's keeping track of what memory is allocated and what memory has been freed. So we can actually go up here, and I can try and see. Yeah, so this was like 203B1 before, and then when it got moved down here, it's now 20391. So it's 20, or it's the previous number minus 20, or minus 20 hex, which is really 32. And so what you're seeing is not just the data that you're working with, but also the artifacts that are built in by the internal memory management system that this system standard library is using. And that's where I'm saying that becomes something that's very dependent upon what compiler and what toolkit you're using. But that's another artifact here, and that's kind of what that pattern is showing. So when you're analyzing memory and looking at the data in memory, those are also useful things to look at to try and follow like dynamic allocation and stuff like that. But what we ended up looking through here was we saw a pattern. Was I would have gotten to a loop of code, and we looked at that in the control flow graph example and stuff. So we looked at the looping code examples. I've gotten to a loop of code, and then if I'm watching memory as it's rerunning through that loop, I'll see this succession of changes where something writes this random value here, and then has it followed up with like a 0 pointer or some sort of indication that that's that it doesn't go anywhere. And then I run through the loop again, and then it adds more information to it. And then I run through the loop again, and it has more information to it. So I have that sequence of steps that allow me to gather that type of information or that kind of programming pattern from the execution that's running. So So I'm going to go ahead and jump to the next slide. So then we'll talk about hash tables. I like to jump to this one after linked lists because really what it is it's just an array of linked lists in a nutshell. Generally how this works, and I'm going to show the code again to kind of choose it, is that you give it a data element to insert into the structure, and then it looks at the data element, runs a function against its contents to decide which one of the linked lists it belongs in. After it finds it in one of those linked lists, then it goes and adds it somewhere in it. So, there's really two data structures that you end up looking at here, which is you end up having this contiguous array, and then you end up having pointers to the linked lists that it's referencing. And then these end up being two things that you have to keep track of. So I'm going to set a breakpoint right here, or actually right here. So, so now we're stopped right there, and what I'll do is I will print HT, and then I get that it shows me, it does a nice breakdown of what I'm looking at, but in some cases it may not be that pretty. So what I may end up doing is I may end up just having to do 16. So it ends up having that. So I can try and show the stuff around it if I want. But yeah, it ends up having it. One of the interesting things here also is that this one, because, whoops, I'll show it over here. When I created this for the first time, I created it by using the new operator. And so it put everything, or I should say it allocated everything from a pool that was reserved for use by the new operator. And that's why you ended up seeing all this data up here lived within this address range. Now, this hash table object is actually being allocated here. And so that's not allocated using the dynamic pool. It's not allocated out of the same pile of memory that new and free and malloc and delete are using. That ends up actually being on what's called the stack memory or the heap memory. So if you remember when we were looking through this, I had this function here, and then what it ended up doing was it executed this operation here, which was to subtract some data, or I should say subtract some, basically 16 from the stack pointer. So it's to move the stack pointer 16 out of the way in order to make enough room to then store these things right here on the stack. So, or specifically these two right here. So these two 8-byte values on the stack. So when we're analyzing code that is utilizing the stack for temporary storage, for temporary variable storage, this is a common practice that you'll see as well. And what that ends up doing is it doesn't end up using the memory that new and malloc or free and delete would use. It ends up using memory that was reserved in the same place for doing like return address pointers and stuff like that. So one of the ways that you can I think it's info registers. There we go. So one of the ways that you can identify this as being the case is that when you're analyzing a program at runtime, you can look at the registers, and wherever this one happens to point tells you where the stack is, the temporary variable stack, and the heap is as far as that's concerned. So I'm able to pull this out that way. So I'm going to go back to the program, and what's going to happen is I'm going to insert the same sequence of elements just into the hash table. And what the hash table does, or I should say what the add to hash table function does, is it creates a new object just like, so all this stuff at the top ends up being the same as it was for linked to list. Then it calculates which one of the 16 hash table buckets it's going to fill. So it's got 16 lists that it can choose from. And the goal here is that if I have a lot of items, I don't have to iterate across all of them to find, say, the last item. So if I had 32 items in my my linked list and I wanted to add a 33rd item, I end up walking or running that loop 32 times in order to insert it. If I don't want to do that, if I want to run it a lesser number of times, I can use an approach like this. And so in this one, depending on how the item sorts out, I may only have to ever iterate across 3 items or something like that. So, but a good indication that something like this is being used is, say, having it pre-initialized with either a large list of zeros or maybe a large list of the same number or something like that. So now I'm going to go and list main again, and actually I don't have to do that, I can just do next, right? So it added this already, and now I'm on this line. As you can see right here, I'm on this line. Oops. So then I'm going to go and show, I'm just going to look at the 16. So I'm going to go and show this hash table. And so now you can see that one of these buckets has been populated, right? So then I'll go next again, and we'll see still just one of them's populated. But if I want to, I can print this. Do that? No. I probably just have to go and do this. So then you can see that I've got this data right here pointing to another thing, and then that thing actually ends up being this one down here. So this ends up being the head of my linked list, because what I did was I looked in the first structure, which is right here in yellow. So that yellow one, that's just a contiguous list of pointers, and then it's pointing at the first element in this top green box. And so then I looked at that, and that one is right here. And then this tells me that the next element is actually down here. And then this tells me there is no other element. Right? So then I can do next again, and I'm going to look at my hash table structure again, and it still shows the same thing. So then I'm going to do next again. I might have ended up putting all of these in the same place. So let's see. Yep. And so there, oh, I know what the problem is. I'm actually looking at, oh no, I'm looking at the right place. Yeah, here we go. So, yeah. So what I was looking at was that this was actually the second bucket. Sorry about that. This is the first one, second one. So there's 8 rows and 2 columns. So first bucket, second bucket, third bucket, fourth bucket, fifth bucket, sixth bucket, all the way down to bucket 16. And then what happened was after I added one, I ended up filling up the first bucket. And then I was running it again. And so after I added, how many do I have? I added 5 items, and there are 3 buckets in my hash table that are used. And then all the other ones go unused for now. And that just happens to be what my hash function is doing, which again, what ends up happening is the array position in here is picked from a hash function. So the sequence of steps that you'll traditionally see would be I'll go up here and show you this. Actually, I will go here and I'll just do I think it's that. Yeah, it's there. Right. Sorry. Okay. So then we'll just do so here's the reference to add to ht. So this is the add to ht function. And so what you end up seeing is you'll end up seeing, say, something that's calling the hash function, and then it ends up taking the result of that and then tries to find a spot where it's going to store it, and then ends up using that later on, which is down here, to then decide where it's going to end up doing a copy operation from, which is, yeah, right here. So then it ends up using, so I'll walk through it again. So what I ended up doing was I passed some data to the hash function. Hash function returned a value that actually, when I'm analyzing this at runtime, ends up being an integer value that's very clearly not an address. Ends up being a very small index number, like a 12 or 7 or something like that. It then stores that in a temporary variable, which is, or in a local variable, I should say, which is pretty common. Then what it ends up doing is it loads whatever this data was into RAX, and then it loads the data that it just stored over here, so that index value. It loads that index value into EDX. And then what this ends up doing is this actually ends up doing a sign extended move. So if that number that I put in EDX was a negative number, you want to, if you're going to expand it from being 32 bits to 64 bits, you're going to need to make sure that you preserve the sign extension. So that's what it's going to do. And then it's going to put that expanded value, so from 4 bytes to 8 bytes, into RDX. And then it ends up using RDX in conjunction with RAX. So it ends up using the result of that hash function down here as an index. And you'll see this construction like this pretty commonly, where you end up having a base followed by index. And if you remember, I showed you that type of addressing mode on one of the slides earlier. And then it ends up, and then it has a scaling as well. So, and then it ends up putting that in our CX. So it's basically getting the data from that location, storing it in RCX, and then it goes and uses RCX later on to go and do the list. Yeah, the list down here. So RCX ends up being where one of the parameters to this function ends up getting stored. Really what's happening here, if you think about it, is the arguments to the arguments to this are some set here. And then I'd have to go back through and walk through it to get a really good idea of what it's doing. It's using a slightly different function calling mode than what we looked at before. But basically, these variable moves you see in front of this are populating those, like, what did I have, 4 or 5 arguments to the function right here. 1, 2, 3, 4, so 4 arguments of the function there. So I'm going to go back to the GDB example. But yeah, so you can see the hash table got built out, and what I can do is I can use the same logic, which is I'm going to go and look at this thing here and see what's in it. And there's some data in it, and it's got a terminal there. And then I can look at some data here and see what's in it. And I can see that it's got data here, and then it's got a pointer here because it looks like a pointer. So I'm going to guess that it's a pointer. And then that actually ends up pointing to this one down here that I actually just happen to have on my screen, which then has more data, and then points to this pointer, which is further down below. So you can see this is CEO or CE0, and this one's DE0. So if I want, I could actually do this and see more. So here is 4. So there we go. There's DE0 right here. So and so I can kind of, I have to use that initial table as my index. And if I walk through the code and look for some of the characteristics, like what I was seeing there, I can try and rebuild the structure. And the big key to this pattern to identify it is that I call, say, a addition function, like this one. I call something to add something to the list, and then it ends up performing some sort of what's usually mathematical operation. So I actually gave it a really, really simple mathematical operation here, which is really just to use the lower 4 bits, or the lower, like, basically this is the modulo 16, if you want to look at it that way, in order to discern what index it should put it into. But it'll give some sort of mathematical function like that. And there's a lot of really common ones that people use. So as you go and see more cases like good hashing functions, stuff like that, you might actually see ones where they're commonly doing a mathematical operation against a really common constant or something like that. And so looking for a small function that does a tiny bit of math work like this, where it takes an input, does some sort of math, and then gives an output, and then that output ends up being used as an index to another function, is a really common way to identify that they're using hashing to try and figure out a positioning. So then binary trees end up being very similar to linked lists. They have 2 kind of next pointers in it. I'm not going to go through the same sequence of steps because we're getting closer to the end of class. But one of the big things that makes them more difficult than the other 2 that we just looked at, although they may bear some resemblance in the problem to the hash tables that we looked at, is that how the data is supposed to be organized or sorted or whatever by the author of the program. The data doesn't necessarily have to be organized that way in memory, and it's actually a lot more common than it isn't. So the big thing here is it just ends up being a data object that has 2 pointers, like this does, instead of 1, like this does. So from the data perspective, you're going to be dealing, like in this case, with an extra 8 bytes, or you'll be dealing with whatever, 16 plus 24 bytes total. So C++ commonly uses a standard template library. There's a little bit more detail behind the scenes on them, but a lot of the kind of core structures that I showed you underpin this system. It's really common if somebody's writing a backdoor in C or C++, especially if they're using these library-provided encapsulators. You'll end up tearing apart data structures that are very similar to what we were working on through some of these handwritten examples. Also in C++, so like the code I put in this source code file here that does really simple hash table implementation, linked list, and binary tree, it didn't take me a huge amount of time to put that together. So for like a seasoned programmer, it's also really common to think up strategies where, if I write the data structure in one way, then it'll be more efficient for my specific use case if I just write it by hand. So you run into that also, but they're all going to be working off of the same basic primitives, which is the data structures that I ran off of, because it's the same thing that everyone learns from data structures class. Understanding those things would be very helpful to kind of making heads or tails of like the really messy pile of data that you're going to end up dealing with when doing memory analysis at runtime. So other languages also, again, are built from the lower level, the core languages. And likewise, they also have a lot of these same elements in them. One of the things I will say with all of these is that in addition to the bare data that we have, they typically end up having more pointers associated with them and even some more metadata that's very object specific. So a really good example is that you might be familiar with is like Java, C#, and Python. All of those languages are object-oriented languages, which means, and they're more object-oriented than C++ is. All of those, the runtime actually has a concept of an atomic object element, and that object itself has a type, and actually has some some core-based members associated with it. So in addition to the data that I want to store if I was to make a data structure in Java that had like those 3 things that I made, in addition to those things, memory is also allocated for the other metadata that's very specific to whatever Java runtime I happen to be using. So that'll be key also when you're analyzing those languages to help give you hints about what the author was intending to do. And in fact, when we do get to that part of the class, a lot of the decompilers that exist for Java and for C# are a lot better at recreating code that is readable to you and reflects probably a closer approximation of what the author wrote than the decompilers that we've been and will be dealing with C++. And that's a large amount helped because the data model in those languages and in the runtime for those languages ends up holding a lot more information about the data being worked with in order for them to do their normal job. So, and that's all I've got for today. So hopefully a lot of the GDB examples are also helpful. When we start dealing with the runtime stuff, we'll also be dealing with the Windows runtime debuggers as well, specifically the ones focused on malware. So we'll apply these techniques to that.